Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Asymptotes River College in Sacramento, California. In this video, we're going to continue forward with inverse functions, specifically the domains and ranges of inverse functions. Again, I'm doing this from the mindset that you've been exposed to inverse functions in your Algebra 2 course, but I do want to take a little extra time here because this is considered to be an education for a college algebra or trig student, not a pre-cal student, and so I want to make sure that I fill in any gaps that you might have. As this theorem states, the range of the function f is the domain of the inverse function, f inverse. Remember that notation right there, just as a big warning, that notation is not 1 over f. Anyhow, you know that just from the previous video you watched, but I just want to say that just in case you missed that. By the way, the domain of your function f is the range of f inverse. Let's go ahead and prove that. So in this proof is built in the idea that your function is 1-to-1. So I go ahead and write out at the beginning of the proof, we're going to go ahead and suppose that f, our function, is 1-to-1, and that notation right there, f inverse, is its inverse. With that statement alone, it opens the door to a few little details that we have learned previously about the definition of an inverse function. Specifically, that if we allow the variable y to equal f of x, or in other words, if when we plug x into our function, the output is y, then we know that if we plug in that output into the inverse, so f inverse of y, we get as an output of the inverse, the variable x. So y equals f of x if and only if f inverse of y is equal to x. Well, now we can actually start into the actual proof, now that we've set up some rules, if you will. So let's see, the proof says the theorem says that the range of our function is the domain of the inverse function, and the domain of our function is the range of the inverse function. That's a mouthful. I'm going to go ahead and start with the second part of that. I'm going to start by defining the domain and range of f. I'll let D stand for the domain of f, and R stand for the range of f. Again, I'm not really making any assumptions here. I just need a name for the domain and a name for the range. The next thing I'm going to do is grab an element from the domain of f, and a convenient element from the domain is going to be x. From here, it's almost as if we're just going to steal the definition of the inverse function that we have up above here. So if x is in the domain, then f of x maps to some value in its range, and we're going to go ahead and just say that maps to y, where y is an element of the range of f. But by definition, see above, just right here, this means that f inverse, maybe I should write it, yeah, I'll just say it this way, f inverse of y is equal to x. That's just from this statement right here. I didn't really change anything. Thus, any element from the domain of x ends up being in the range of f inverse. Now, a lot of people will look at that statement and say, okay, great. You're just saying that the domain, D of f, must be the range of f inverse. I'm not saying that. I'm saying if I have an element in the domain of f, it is going to be in the range of f inverse. However, I'm not saying every element in the range of f inverse is in the domain of f. That comes a little bit later. Now, by a somewhat similar argument, since x was an arbitrary element from the domain of f, and it led to a value in the range of f, And we're saying, by definition, we can plug that value that's in the range of f into f inverse. We could say the entire range of f is part of the domain of f inverse. And I've written that down below just to kind of cement that. But I also want to show an illustration before we continue, because I think some people, again, are going to think that I've just proven that the domain of f is the range of f inverse and the range of f is the domain of f inverse. I haven't yet. To illustrate what I'm talking about, let's go ahead and look at a little picture I've just drawn here. So again, we've mentioned that if we have an element in the domain, then f of that element will map to the range of f. Well, here's an element in the domain, and f just carries that element all the way over here into this bucket, which we'll call the range of f. And by definition, f inverse of that element should equal x. That is, f inverse will take that element and map it all the way back to x. And right there you think, well then, since x and y were arbitrary, that should cover all bases. It should be that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. And you're kind of right there. It is true, but I want to shore up any doubt. What if, for an example, there was a rogue element in the range of f there, and it did not get mapped to by f? In other words, there wasn't an input in f that led to that rogue unhappy face. So none of these little dots here in the domain of f, and I'll write it this way, domain of f, why not? None of those elements map over to that unhappy face. Well, then unhappy face wouldn't actually be in the range of f, to be very honest with you. So really, when I was saying earlier that this doesn't really prove it, it kind of does prove it, that the domain of f is the range of f inverse and the range of f is the domain of f inverse. I just wanted to clarify that there is no such thing as an object in the range of f that does not get mapped to by some element in the domain of f. If there's an object in the range of f, it must have been mapped to by some element in the domain of f, period. That's by definition. So therefore, these buckets, domain of f and range of f, exclusively contain the inputs of f and the outputs of f, and nothing less and nothing more. Yet for every output of f, there's a corresponding input. So therefore, just to allay any concerns, it is true that every object in the range of f is born from an object in the domain. And now we can actually map that guy over. I'm going to go ahead and just map him using this nice highlighter all the way over to there. Now, if you really want to shore it up, you can argue the opposite direction, but I'm not going to do that actually. I think we spent enough time on this, so we're pretty good at this point. I'll go ahead and move on to some examples. I stole this from the text. I think this is a decent how-to. And again, I don't like to talk about how-tos. I don't like to give recipes if something is new to you. However, inverse functions are not new to you. You've seen them now, at least in one full course. So therefore, I'm okay with teaching you a little trick every now and again. So here's the how-to or the recipe for this. Given some function, and what do you do if you're asked to find the domain and range of its inverse? That's actually not too terrible. If the function's 1-to-1, just write the range of the original function as the domain of the inverse, and write the domain of the original function as the range of the inverse. I will tell you right now though, finding the range of a function is generally more challenging than finding its domain. So we will see that as future examples come up. Another thing you need to know, if the domain of the original function needs to be restricted to make it or force it to be 1-to-1, then this restricted domain becomes the range of the inverse function. And again, that will be something big later on. I might even just make an example off the cuff here in this video just to showcase that. Now, without stating the actual inverse, state the domain and range of the inverse function if the function we're handed is 2 raised to the x minus 4, then minus 1. If you're watching this video series in the order with which I've recorded them and I present them, then you should note I have not covered exponential functions yet. However, exponential functions are prerequisite for any college algebra course, so it is assumed that you've been exposed to exponential functions. This is why I like to kind of sneak them in early lectures, just to remind you that you are responsible for knowing these functions. Do not worry if you feel like you need to review that material. We actually do a little bit later on. So let's go ahead and figure out what the domain and range of the inverse function is if our function's 2 raised to the x minus 4 and then minus 1. The easiest way to do this, in my opinion, is to graph this exponential function. Most exponential functions in the natural sciences kind of look like this. That style of exponential function occurs if the base of the exponential function is greater than 1. So this would be like a 2 to the x, in fact. So that's what 2 to the x would look like. It actually goes through 0, 1, and 1, 2. Now I'm just going to take advantage of transformations of functions to rewrite this, or regraph this, I should say, using transformations, shifts specifically. So if you look at our function we were handed, instead of 2 raised to the x has been manipulated. It is now x minus 4. And x minus 4, as you have seen a previous video of mine about transformations, x minus 4 becomes 0 at 4. So I know that this graph has been shifted to the right 4 units. And of course, the minus 1 on the outside just means it's been shifted down 1 unit. Something you should know about exponential functions is that they have horizontal asymptotes. Those horizontal asymptotes occur on the x-axis. If you have some vertical shift up or down, that horizontal asymptote will also shift up or down. And in this case, since we're shifting everything down 1 unit, my horizontal asymptote is actually shifted down 1 unit. So here's our new horizontal asymptote at y equals a negative 1. And then I'll plot these 2 points with the adjustments. So I'm going to add 4 to the x value, 1, 2, 3, and 4. And let's see, I'll bring the y value. So remember, the point was at 0, 1. Now it's at 4, 1. However, I'm going to subtract 1 from the y value. So now that point is actually at 4, 0. 1, 2, this point right here. Again, I'll add 4 to its x value to become 5 and subtract 1 from its y value to become 1. So 5, 1. Let's just park that right there. 5, 1. And now I'll just connect those dots and make sure that I have an exponential looking function otherwise. Now you might be thinking, wait a second, weren't we supposed to be just asking or stating the domain and range of the inverse function? Yeah, but what's critically important is to find the domain and range of the original function first and swap them, and that'll tell you the domain and range of the inverse. So for f, the domain, what you can plug into f, is all real numbers. Any x value you want can be plugged into an exponential function. So the domain of f will be the set of all real numbers. On the other hand, the range of this picture, well, you can see because we have a horizontal asymptote at negative 1, this exponential function will never actually touch that horizontal asymptote. And so our graph does not actually achieve a y value of negative 1, but it gets really close to it. And it climbs all the way up to infinity. So that's our range. Just from that, I could tell you f inverse has a domain, which is the range of f. So the domain is -1 to infinity, and the range of f inverse is the domain of f. It's all real numbers. So you swap them. That's it. It's very nice, but not too terrible. As a final example, at least in this video, let's show that these two functions right here are not inverses, but can be forced into inverses by using a domain restriction on f. Now this should be new to you. You should not have seen this in an Algebra 2 course, mainly because domain restrictions on functions are more the purview of pre-calculus, college algebra, and calculus itself. So let's see why these are not inverses first. Recall from a previous video, in fact the one prior to this, that if you have a function and its inverse, then you can compose those two functions, f and f inverse, and it will always return the original argument. That is, f of f inverse of x should always just be x. They should undo one another. And f inverse of f of x should be x. Again, they should undo one another. So if these are actual inverses, then I should be able to take f and plug g in, and it should become x. Likewise, I should be able to take g and plug f into it, and it should become x. I happen to know how this is going to work, so I'm going to choose, actually, you know what, I'll just choose the first one. So let's go ahead and work on the first one. F of g of x. Let's just see what that is. Again, if they're inverses, it should just turn out to be x. Well, this would be f of, actually, let me go ahead and write it that way. F of, well, g of x is negative square root of x plus 1 and then minus 3. So I'm going to take that argument and plug it into the function f. Remember, f is something plus 3 in quantity squared and then minus 1. That's what f of x is. That something we're going to replace with negative square root of x plus 1 and then minus 3. To do that, I have to give myself a little extra room here. So I'm going to erase what I just wrote just so that I can give myself the room. So I get this. That's the argument. In fact, if you want to see that in a different color, let's do that. So all I'm doing here is I'm just saying the argument for f, which is g, I'm writing in blue. Now f itself, I'll keep in black, but again, the argument, what I'm plugging into f, I'll write in blue. So negative square root of x plus 1 and then minus 3. And then the rest of the stuff that I'm writing is actually just the natural stuff that occurs within f. Now let's clean this up, a little algebra here. As I tell my calculus students, you should always do arithmetic before you do algebra, algebra before you do trig, trig before you do pre-calculus, pre-calculus before you do calculus. And the reason why I say that is I want you to know you work your mathematics from when you learn things until today. So if there's something that you learned a long time ago, like early in your mathematical career, like called arithmetic, you should perform that before you perform all the complicated stuff. Our arithmetic here is negative 3 plus 3. So we get this beautiful negative square root of x plus 1. That's being squared, minus 1. And then we're going to square that. Well, squaring the negative, that becomes positive. Squaring a square root, that cancels, and you get x plus 1 minus 1. A little arithmetic in the end returns x, and we rejoice. That is awesome. We feel as though these are inverses. But are they? Well, we'll find out. Let's check it the other way. G of f of x. Again, if they're inverses, g of f of x should just return x. I will write the function g in black, and f I'll write in blue. F is x plus 3, quantity squared, minus 1. Again, I'll just plug that into the function g. G, remember, was a negative square root of something plus 1. That something is the blue ink, and then plus 1. I didn't need that radicand, or the radical, to be that large. So just erase that. And then remember, we have this minus 3 on the outside. That's G. Well, zooming into that, let's do a little cleanup. Arithmetic, right? So this is going to equal negative square root of the quantity x plus 3 and quantity squared, and then minus 3. And here is where a very critical thing happens. There's a theorem that you learned way back in Algebra 2 that most students often forget, honestly, because it doesn't come up after you learn it. It's taught to you and then you move away from it and you never see it again. But it is incredibly important from this point forward. And that theorem goes like this. Suppose that you had the square root of x squared. In fact, let's not call it x because I'm using x in this problem. Let's make the square root of happy face squared. You would think, and most people would argue, that that is happy face. So I'm going to put a happy face there, and I'm going to put a question mark here. And I'm going to challenge you to think, is that actually true? Let's put on our critical thinking hats here. If I said, what's the square root of the quantity 3 being squared? Well, you know it's the square root of 9, which is 3. So yeah, the square root and the square just cancel each other out and you get that 3. And you say, see, I told you so. So the square root of happy face squared is just happy face. Until I give you this example. Square root of the quantity of negative 3 being squared. Well, negative 3 squared is 9. Square root of 9 is not negative 3, it's 3. Notice that negative 3 is not the same as positive 3. So in this case, the square root and the square did not cancel each other out. Or if they did so at a cost. The cost was forcing an absolute value. And that's exactly what the square root of a square does. It forces the absolute value of whatever your argument was. Again, because a square root will never return a negative number. Even if you had a negative number squared and then took the square root of it, square roots will never return negative numbers. That being said, if I go over here and I see, oh, I have a square root of something squared. And you say, well, I just learned that that is not going to be x plus 3, but instead the absolute value of x plus 3. And notice we're stuck. We're stuck because we don't know if x plus 3 is positive or if it's negative. So therefore, g and f are not inverses because g of f of x is not actually x. We need to modify our function f to force it to be invertible. Now, knowing that these are not inverses of one another, we need to make a modification. And the easiest way to see that we need to make a modification is just to look at the graph of f itself. F is a parabola. When you graph it out, it's been shifted. Let's take a look at this. It's been shifted to the left 3 units and down 1. So it's a parabola shifted 1, 2, 3 over and down 1. Looks something like this. I don't need it to be exact. I just need to take a look at it. And you should be able to tell by that curve right there that this function is not one-to-one. Now, we haven't actually stated why in a theoretical format. I haven't stated a theorem or anything like that. But let's just ask, why is that? I mean, it totally is a function, right? Each input, like the input of -1, leads to a single output. And you can play this game with any input, right? That input leads to one output, and so on and so forth. All the inputs lead to a single output. So this is definitely a function. Nobody's questioning that. What we are questioning is it one-to-one? That is, does every output lead back to a single input? So for example, let's pretend that this output is a height of 10. It's not, but let's just pretend it is, okay? So does this output of 10 lead back to a single input? You say yes, and I say no, because here's another output at the same height that leads to a different input. And that's a problem, The problem with our function is that it's not one-to-one to begin with. We need to force it to be one-to-one by erasing part of it. So which part do we erase? Well, we want to erase the part we want to erase enough of it so that each y value only comes from one single x value. So the way you can go about this is a lot of people will just start erasing part of the graph, which is exactly what you should do. You start erasing and you look at this, you maybe get down to here and you say, now is that one-to-one? And the answer is no, because again, there's a y value at this height, which leads to two different x values, right? There's a height on the curve that leads to two different x values. So that's not going to work. So you keep erasing. Will that work? No, still it won't work because there is a y value right here that has two inputs that lead to that same output. And so you get kind of this idea of, oh, if I continue to erase until I get to about there. Whoops, I didn't mean to erase all that though. So, but if you get to about there, you could see that no longer are there multiple y values that lead to this x value, or that, I'm sorry, there's no such thing as a y value that leads to multiple x values. This y value stands alone, leading back to that x value. This y value stands alone, leading back to that x value, and so on and so forth. So each input has an output. Each output has a single input. Let me say that again. Each input has a single output. Each output leads back to a single input. However, so this is definitely one-to-one, by the way. But is it the right one-to-one function? That's the real question. Well, you only had two options, honestly. So if you're staring at this going, oh my gosh, this looks so hard, it isn't that bad, because all you need to do is graph your original function, which we did. I spent a lot of time doing this other stuff, but the reality is I could have skipped that and just said, all right, let me go ahead and graph this function f and determine, is that one-to-one from the get-go? And it wasn't. So I knew that I needed to erase half of it. So I just want to make sure, did I erase the proper half? Just in case I didn't, I'm going to go ahead and draw in green here the half that I erased so that we just consider both possibilities. So let's see. Let's suppose that we keep the blue half. That is, when x is -2, let me point an arrow at that. When x is -2, our output should be 0. That's what it looks like. Let's see if that's actually true. Let's go to our function f up here. If you were to plug in -2 plus 3, that's 1. Square it, that's still 1. Subtract 1, and it's 0. Okay, great. Now that we've labeled this point, -2, 0, we know that point exists on this curve. By the way, there's a symmetric one over here. I'll write it in green. This point is -4, 0. The inverse function should swap the roles of x and y. Remember, the domain of f is the range of its inverse. So if -4 is in the domain of f, then -4 must be in the range of the inverse function for f. And if the corresponding range value for -4 is 0, when you're talking about f, then the corresponding the corresponding domain value would be 0 in its inverse. That is, easier way to say it, f takes -4 and trades it into 0. Its inverse had better take 0 and map it into -4 if we were doing the green part. If we're doing the blue curve, then the function, well, it takes -2 and turns it into 0. Its inverse should take 0 and turn it into -2. So let's see if the blue curve will work as the inverse function, specifically the inverse function they've handed me. So we're going to see if when we plug 0 into g, does that turn into a -2? Well, let's find out. It's a negative square root of 0 plus 1 minus 3. Or in other words, -1 minus 3, which is a -4. So 0 does not map to negative 2. So that's a problem. That means that this blue curve is not the curve we want. Now, it doesn't really mean the green curve is the one we want, but let's go ahead and find out. So again, going to this green curve, remember, f takes negative 4 and maps it into 0. The inverse should take 0 and map it into negative 4. Again, because the domains and ranges swap. So let's go ahead and see if g is the inverse here. Let's go ahead and say, or ask, does g of 0 map to negative 4? And we've actually just seen that it totally does. Check. So we are going to keep this green branch because that means that's the proper domain restriction. We're going to restrict our domain to be, so the domain of f, we're going to restrict to be from negative infinity all the way up to negative 3. It's okay to include negative 3 in that. Now you can actually show that these two are inverses. Now I do want to again repeat something here. From the get-go, reading this problem, you could have just said, okay, I need to show that these are inverses, but they're saying that they're not inverses, but can be made into inverses using a domain restriction on f. Once you read that, you should just say, let me graph f. So you graph f, you get this parabola that we originally had, kind of like this, and you say, well, that's not invertible. It's not 1-to-1 because this y value right here leads to multiple x values. So I'm going to have to erase one of those two branches. The way you figure out which branch to erase is to just plot a point on each branch and ask yourself, if I reverse those values, well, you could check that. You could plug 0 in to your function that's supposed to be made into the inverse, plug that in and see what happens. That's what we did up here. And we plugged in, we got negative 4. Not negative 2, but negative 4, which tells me the branch I'm going to erase is the one that doesn't contain negative 4. So I'll erase this junk here. Whoops, I wanted to keep the domain on there. But I'll erase all this other junk. And there is my domain restriction. All x values from negative infinity all the way up to negative 3. And if you want to check at that point, so again, I didn't even bother touching any of this stuff during this entire conversation. Now, so if you want to now check to make sure they're inverses, you could say, well, let's go ahead and look at g of f of x, because that was the one that caused the issue. So I'm just going to check that one. And you go over there and you say, well, g is negative square root of something, right? And that something is something plus 1 and then minus 3. The stuff you're plugging into that is f. Well, f, remember, I'll write it in blue, is x plus 3 quantity squared minus 1. Again, do some arithmetic. You get this negative square root of x plus 3 quantity squared and then minus 3. And you remember, oh yeah, shoot, that square root of a square returns the absolute value. The second thing you should remember about that is the absolute value returns one of two cases. If that happy face was already non-negative, you could rip off the absolute values. If that happy face was actually negative though, the absolute value will return its opposite because absolute values want to return positives. So the absolute value will return the opposite of happy face if happy face was negative. That should make sense. So the question is x plus 3 positive or negative? Well, let's look at our shaded region. Our x values go from, I'm going to go ahead and highlight it, negative infinity all the way up to negative 3. So grab any x value you want and just check to see if x plus 3 is negative. Plug in negative 4, for example. If you plug negative 4 into x plus 3, well, that's a negative number. So I happen to know that this will totally return the absolute value of x plus 3, first of all. But x plus 3 is definitely negative. Why? Because x, well, it's definitely not positive. Why? Because if you subtract 3 from both sides, we have our domain issue, or domain restriction. X is less than or equal to negative 3. So I happen to know that x plus 3 is negative, which means the absolute value is going to return the opposite of x plus 3. Negative times negative is positive. 3 minus 3 is gone. And you get to your fancy little x. These are definitely inverses now. Now that was a very drawn out and honestly convoluted example. But this is where we're heading in mathematics, really. If you aspire to get into calculus and pre-calculus, you must be able to work problems like this and do domain restrictions and understand why domain restrictions exist. Now, could this have been done easier? Yes, absolutely. But I want to kind of work through the theory first. All right, so we'll see examples like this in future videos, but we'll invent ways that kind of speed the process up. But for now, I want you to spend some time thinking about that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.